Thank you very much, Mia, for the kind introduction and for the invitation. It's a pleasure to come to Beijing again, online, of course, during this day. So last time I was in Beijing was 2014. That's quite a while ago. So maybe it's time to, well, get there in person again at one point. Yeah, so today I'm officially the T from ASD, maybe, if you want me to, that's fine. But today I'm talking about something slightly different, although related. So kind of a main result will be some cellularity, if you remember last week's talk, of a certain type of algebras. Strictly speaking, it will be a more general version of cellularity, which I'm not going to elaborate too much on. But kind of this main idea is of cellularity, in case you don't remember, is that it's kind of a nice, easy way to write down a certain basis, and the basis is adjusted to multiplication in the algebra such that you can kind of read off the simple representations, the irreducible representations for the specific algebra. And the algebra I have in mind today is called the KLR algebra, or a little bit more general, what I will call a WKLRW algebra, so WKLRW algebra, so weighted KLRW algebras. And kind of the main story is they will kind of, you should think of them as being a very general version of a certain type of algebras that generalize several algebras you might know from modern representation theory. If you don't know them, it actually doesn't matter. You can take the weighted KLRW algebra, so the one I'm going to explain, as a definition of those algebras if you want. But the point is, and we'll see that anyway, that they generalize quite a few nice algebras that you might have seen before. Okay, I should have said already a long time ago, but luckily it's on my slide. So I'm reminded here that this is all his joint work with Andrew, and it's fairly recent, so something like December or November last year, I forgot. It's too long ago, I don't remember anymore. And kind of our hope here in general is that we can push this quite far. So I'm only going to talk about specific types. We'll see what that means in the end. But I think this story is really, really general and seems to be a really, really powerful approach to say something interesting about certain types of algebras, like those KLR algebras. Okay, but it's not necessary for this talk to know anything about those algebras. I'm kind of trying to explain in a few slides the more general KLRW algebra, and you can, if you don't know KLR algebras or whatever, you can take, as I said, KLRW algebras as a definition if you want. Okay, but KLR algebras are actually around for quite a while by now. So they were roughly introduced in 2008, referring to kind of archive versions here. They were around implicitly in the literature earlier, so maybe kind of the first reference would be something like Arrighi's categorification theorem, which is a kind of a famous theorem in this story, which goes back to the mid of the 90s roughly, realizing certain canonical basis of affine Lie algebras using cycloatomic algebras. But nowadays, kind of the point is that KLR algebras, and I just say KLR algebras and friends, I will be a little bit more precise in about 20 minutes or so. But there's this whole business of KLR algebras and various algebras along those lines. There are also categorified quantum groups and whatever. And they all fit into this nice setup of categorical representation theory, this modern version of representation theory that actually came out mostly out of Rouquier's original work. So the way to read this, by the way, is so there are two papers, a Kovanov-Lauder paper and a Rouquier paper, which appeared roughly about the same time. And they did roughly the same, just using a very different language. Anyway, so they introduced those KLR algebras. That's where the name comes from, KLR, so Kovanov-Lauder Rouquier. And nowadays they're really known to many parts of modern representation theory and mathematics in general. So the original story was of Rouquier's original idea was to categorify certain Cauchy-Moody algebras associated to certain quivers. So think of Lie algebras or GLN, SLN, something like that. And the KLR algebras categorify the positive half of those. So very nice relationship, and also categorify their integral representation, their highest rate representations. Covenant-Lauder came from a slightly different point of view. They were more interested in the end in some version of low-dimensional topology. So this question, link homologies, and you try to, so link polynomials come from some version of quantum groups, and link homologies categorify link polynomials. So link homologies should come from some version of categorified quantum groups. And if you push that idea far enough and you are very smart, like Covenant-Lauder, then you will end up with the definition of a categorified quantum group, and a special case of that is the KLRW. Then later, people realized this amazing connection to using basically a graded version of Araki's categorification theorem to graded representation theory. So you can actually use the KLR algebras to find interesting gradings on very well studied and very well known categories in representation theory. So categories associated to symmetric groups. So representations of symmetric groups are actually graded using the KLR setup. This idea has been very successfully applied to various different algebras. So not just symmetric groups, but kind of a lot of algebras in representation theory have a KLR analog, and the KLR is naturally graded. I'm not going too much into details how it's graded, but then you can kind of push the grading from the KLR to your favorite algebra, for example, the symmetric group, and you get graded representations, which is pretty cool because you can make statements about, let's say, simple modules are symmetrically graded. So if you think of a simple module L and you want to know its dimension, then you can kind of calculate its graded dimension, and the graded dimension of a simple module will be palindromic in the grading. So you can have something like whatever, if I write V for the grading, it would be something like V plus V inverse. So this is of dimension 2, one element, one basis element in degree 1, one basis element in degree minus 1. That's the notation, and you could show actually that these are palindromic, right? So if you have V to the 12th and you have 5 times V to the 12th, then you have also 5 times V to the minus 12. That's really nice palindromic symmetry, and this tells you extra information about those representations of symmetric groups in this example that weren't accessible before, which is pretty amazing. It's a huge story. The key word here is the Brandon-Klashev isomorphism, which is, if you want, in hindsight at least, just a very explicit version of Araki's categorification theorem, if you want to. Anyway, there are many more stories that are nowadays related to KLR algebras, which I'm not going to talk about because I only have 1 hour in the end, but it's really a huge theory. And my main problem that I kind of want to address today, so, well, if it wasn't clear, I would like to study KLR algebras somehow. The problem is these are really, really complicated algebras. So I'm going to show you a generalization, which is not much more complicated, but still very complicated. And this is really a huge drawback. So not much is actually known about these algebras. For example, those questions, for those of you who were there last week, cellularity is, so KLR algebras are attached to any Kac-Moody algebra.
The recording has stopped.
Okay. So KLR algebras are attached to any Kac-Moody algebra, and you might ask in which cases they are cellular, and it's basically not known. So for type A or something, it's known, but not much more is known about those algebras. Turns out that they're really, really new algebras as soon as you leave type A, the type A situation, and that's not really all that much, Certainly some people at the BIT have worked on those algebras as well. We will get some references as we go along. But this is kind of my setup here. There's this slightly mysterious and relatively new family of algebras which I would like to understand better, and kind of almost nothing is known about them in general because they are so complicated, which is expected if you believe my little diagram here that you see, because it just connects a lot of very interesting mathematics. Okay, so how can I actually approach this problem? And this is kind of where the new idea comes into the game. So roughly I want to do the following trick, and that's what I would like you to keep in mind all the time. So in the end I would like to study an algebra of this type. Well, the dual numbers, this algebra is called the dual numbers. It's one of the easiest non-trivial algebras you can imagine. Something like a polynomial ring and you quotient out by y squared. So polynomial ring in y. This is a two-dimensional algebra and it's already relatively interesting. Okay, there's another two-dimensional algebra, which is on the other side. Let's say over the complex numbers. So this is Z mod 2, if you want. So y squared minus 1. If a quotient y squared minus 1, this is a semi-simple algebra. Okay, so let's say I would like to study the blue one. So what can I do to study the blue one? This is a toy example, of course. You might say, okay, I can just study the blue one by hand. Sure, in this toy example you can. In general, for KLRW, it might be a little bit more complicated. So in this toy example, I can try the following approach. I can write down a much bigger algebra, or seemingly much bigger algebra, in huge quotation marks here, where I just split the roots of the polynomial using some variables, a and b. Right? So if I specialize both to 0, I end up here. If I specialize both variables to 1, I end up 1 and minus 1, the two different roots, I end up on the right-hand side. So in some senses, interpolating algebra at the top looks more complicated, but at least then controls both of those algebras, the blue one and the red one. And somehow everything you can say about the big algebra, somehow you could push it along the arrows and you get new results about the small algebras. And in some other sense, it's actually easier, the top algebra, because now you just have split the roots and you just have variables for the roots. Remember, roughly, if you like this analogy, where you do the same trick is if you think about Galois theory and you would like to study roots of polynomials, that's usually very hard to compute Galois groups of polynomials. But if you do the generic case, where you just have generic variables, it's fairly easy to see that the Galois group is Sn. And then you can prove various theorems about it, like you can't solve polynomials of higher order degrees, so 5 or more, because you get Sn. In some sense, then it's easier because you have variables instead of explicit numbers. Kind of the same happens here. So this top algebra is actually easier than the bottom two algebras. It's a bit surprising, but if you've never seen that, you need to believe me at this point. You can try it yourself. The top algebra is actually easier, although it looks more complicated. And the point is, what I would like to do is, I would like to play this interpolation game with scalar algebras in a slightly funny way. I need to set up the whole notation. It will take a while, and it will involve planar geometry. It's kind of a fun game. So I will really use the geometry of the plane to play this interpolation trick with my polynomials as in the top box. And this algebra that comes out is this weighted KLRW algebra. And we'll see how that works. So it's kind of the trick. So you should think of this one here as the weighted KLRW algebra, this one is a KLR algebra, and this one is kind of a semi-simple version of everything. And all of them will appear in my setup. Hopefully that's kind of clear, right? I want a big algebra, and the big algebra will tell me new information about the smaller algebras, which I'm actually interested in. And the advantage of the big algebra is it's kind of easier to manipulate. Okay. A little bit careful, there's a slight catch. The story is not perfect, for example, and also my story in the end is not perfect. So for example, you can almost pass everything from the big algebra to the small one, but there are some subtleties. For example, the big algebra, you can't just really push the simples, the irreducibles, to the small algebra, because this has just one irreducible, given by specializing y to 1. And this needs to have 1 or 2 irreducibles, because it needs to specialize to those two. And this is Z mod 2, so it has actually 2 irreducible representations. And this has just 1. So let me just write 1 and 2 here. So the big one somehow needs to, you lose some information in the specialization process. So point is, most interesting results, like cellularity, you can actually read it off from the big one. For more fine, refined statements, like whatever, dimensions of simple modules or number of simple modules or something like that, you need to work a little bit harder. Anyway, so the same is just true for all the algebras we see today. Just keep that in mind. It's a nice approach. It gets you a lot actually for free, but not everything. Right? So just keep that in mind. Okay, so this is the setup. I haven't explained anything right now. It's just the overall setup. The overall strategy is to kind of interpolate this mysterious scale algebra, because it's people like it. People like to study it. I'm one of those who like to study it, but it's so hard that you really need to come up with some strategies to talk about those scale algebras. Okay, to get us started, I need to introduce now the weighted KLRW algebras, and I will do that step by step. So it will be a lot of combinatorics. I try to be as slow as possible. Don't worry if you don't get everything. It's not so important that you get all the details. It's more important that you get an overall flavor how to do it. And the first step I would like to do is I would like to talk about string diagrams. If you haven't seen those before, here's how it works. It's kind of a magical way of writing down algebra in terms of diagrams. So I'm just thinking about a very simple case here, the symmetric group S8 on the set 1, 2, 8. And all you should do is, instead of writing down algebraic formulas, you can write down those funny diagrams. I just label my strings from bottom to top. So I just label my strings from left to right with my elements of my symmetric group here. So 1, 2, 3, 4, 5, 6, 7, 8. And I can now read off the permutation. So 1 goes to the second. This is the second position. 1, 2, 3, 4, 5, 6, 7, and 8. So 1 goes to the second position, 2 goes to the fourth position, and so on. Let's hope I've done this correct. So 1 goes to the second, 2 goes to the fourth, 4 goes to the third. Looks not so bad, and 3 goes to 1, and so on. Right? So you can just write down a nice diagram for every permutation. In this case of 8 numbers, but of course this works for any numbers. Here's another example. Hope I haven't messed up. So 1 goes to 2, 2 goes to 4, and so on. 4 goes to 3, 3 goes to 6, that might be correct, and so on and so on. Okay, so those guys are called string diagrams. They really have been around for donkey's years, so God knows how old those are. But it took a while until people really used them extensively. Mostly with the breakthrough in the 80s when quantum topology or quantum algebra was born, and people like to just write down diagrams for symmetric groups in this case. And the KLR algebra and the weighted KLR algebra will be based on this idea. By the way, I'm not saying that diagrammatics wasn't around before the 80s. It was just not very well known. Some sense this goes back to Feynman or Penrose 40s, 50s, 60s of the last century. So in some sense this is really well known, and in some sense this is really new. Depends a little bit who you ask. But in the symmetric group case, I find it personally really, really powerful. So very, very easy. You can now multiply those diagrams with the following easy procedure. You take the first diagram, so this is my multiplication symbol here. You put it at the top. You take the second diagram. Whoop, here you go. And you put it at the bottom, and you get a new diagram. For example, the first strand here goes to the fourth position, and you just straighten it out. First strand goes to the fourth position. Let me try another one. The seventh strand goes to the eighth position, and so on. So just really, really easy multiplication rule here. Just stack diagrams. The only confusing point is that you somehow need to be careful with your conventions. So I hope I was careful enough, and in my conventions, the left element goes on the top and the right element goes on the bottom. If not, I apologize. I hope that's correct. And you can read off the usual multiplication rules. So the identity element, for example, is just plain strands, right? You can just stack it on top. It won't change anything. Associativity is immediate in this picture. It's kind of beautiful here. So if you ever have problems trying to prove associativity of whatever kind of algebra, try to find a diagrammatic presentation, and it's usually pretty obvious. And well, you take everything modulo certain generators and relations, so you can formulate everything here in the symmetric group. Generators just the simple transpositions, just a little crossing, and the relation are the famous Reidemeister relations. Well, not really for knots, but for those diagrams. That's all you need. So if you like the algebraic notation, then this would be something like sigma I squared equals 1. And this is the type of the braid relation. So I just call those guys sigma I, where this is the I strand. So something like sigma I plus 1, sigma I equals, and then you just turn it around, sigma I plus 1, sigma I, and I'm running out of space, sigma I plus 1. So the famous braid relation. In diagrams, they're just called Reidemeister relations. Okay, so this is a diagrammatic version of the symmetric group, and turns out to be Really powerful way to think about symmetric groups, and has been exploited quite a lot. So a lot of algebras nowadays are just some version of this calculus. Usually more sophisticated, we'll see that, but some version of this calculus. Okay, let me here pull out a bait here. So in diagram algebras, that's kind of the point if you have never seen this. A lot of things just become visually clear. You can just read off properties instead of worrying about equations. In case you like equations, it might be a little bit unsatisfactory, but the point is long equations usually become really, really easy in those diagrams. The catch is that this is not really using any planar geometry. Strictly speaking, it's just the usual algebraic expression. Just write down algebraic symbols, but instead of writing algebraic symbols, you just write down different symbols, which look like string diagrams. So actually, it's just algebra written differently. So this is not doing any magic, it's just writing different symbols, which is good in some sense, but it's also a little bit unsatisfactory because it looks like there should be some planar geometry involved, but in the end it really isn't. It's just a different way of writing down exactly the symmetric group in this case. Okay, and the idea that defined the weighted KLRW algebras is that you actually can define an algebra which definitely depends on the distance in R2. In particular, the algebra I'm going to define, I can't write down a nice generator relation presentation in the classical sense, like for the symmetric group, because you will see it's quite a huge algebra, and it depends on various distances between various strings, as a lot of generators and there's a lot of relations. But in the end, it's just easier because somehow you can completely use your planar intuition, so planar geometry intuition, pulling around strings in the plane to actually say something about those algebras, and those algebras generalize hard algebras from modern representation theory, which is actually a pretty cool approach. So they're really planar geometrical pictures for symmetric group diagrams. Okay, so that's the bait and the catch, and now I'm trying to explain what those algebras are. As I said, if you get lost in the combinatorics, the overall idea is what matters. The combinatorics is a little bit tricky. And actually, what I'm going to show you should work for any type of diagram algebras, if you like those, if you've seen any, but I think nobody has explored that so far. Fine. So, well, it would be a nice project for the future. Anyway, so this is how it works. I really just draw the same diagrams. This is so I just copied the diagram from my previous slide, from my symmetric group slide, and made it a little bit more complicated. But it's really just the same diagram. So the only difference here is from the KLR diagrams, for those swing diagrams, to the symmetric group diagrams, is that now I have different types of strands. You can ignore the red strings, they won't play a huge role, but if you know something like a level in the setup, the red strings will encode the level. More importantly or at least more importantly for today, are the blue ones, which are the solid strings. Maybe I should mark them in blue. So blue ones, I have how many here? 1, 2, 3, 4, 5. I have 5 blue strings here, and there are certain types of ghost strings. They're just called ghost strings, which are those dashed strings. So I have 2 of them here. Okay, so I'm using now diagrams, with string diagrams as for symmetric groups, just with funnily colored strings. Okay, fine. That's so far not a big difference. A slight difference, which you can ignore for most points, is that I also allow dots on strands, which move freely as long as they don't change topology. So you can't pull this dot here over this crossing. This is a non-allowed operation, but you can move it just around its own string. And this is just a combinatorial way to decorate those strings. Okay, fine. And you can kind of ignore dots. And more importantly is, okay, my strings are coming 3 different types, but they're also labeled, and they will be labeled by certain numbers. And those numbers, whatever, here's some labels, they will be the vertices of a certain quiver. Okay, so there will be a certain quiver in the background, and you label your vertices by, your strings by vertices in the quiver, and then the relations of this algebra will depend on the quiver. We'll see an example in a second. And otherwise, it's really just symmetric group combinatorics. Just the diagrams are a bit fancier. Okay, so let me repeat. So symmetric group diagrams take the same ones. Color the strings in solid, ghost, or red. Ignore the red strings for most part of this talk. And color the strings or label the strings with certain numbers, and the numbers will be elements from the set of vertices of a quiver. The underlying type will be encoded in basically in the labeling of the vertices. Okay, so far pretty harmless, not so bad. Symmetric group diagrams a little bit more fancy. That's what it is. So far no difference. So here are some examples of quivers. So as I said, the strings are labeled by vertices of a fixed quiver. Here are some examples. Whatever kind of quiver you like will work. Kind of anything you can associate to a Kac-Moody algebra. Finite type quivers, affine type quivers, anything you want. Strictly speaking, I should fix an orientation on those quivers. So something like this. So there should be some orientation here. But the orientation only determines certain signs, and the algebras will be isomorphic for different choices of orientations. So I kind of ignore that. Okay. And the relations of this algebra, which I'm not going to show you, there are quite a few of them, but they're Reidemeister type relations, and they depend on the quiver. So instead of just, for example, here, instead of being able to pull those strings freely apart, if they are connected in the quiver, let's say you would be in this situation here, that I already have up here, then actually, instead of pulling that apart, you get some error terms floating around. Alright, so the relations of this algebra, which are obviously hugely important, but don't fit on the slide, so I don't want to discuss them, though they're not that important in the end, are really the Reidemeister relations, slightly deformed depending on the quiver, which is actually quite a cool setup. So depending on the quiver, what you get is, or what you have is, a symmetric group type algebra with some labels depending on the quiver and relations depending on the quiver. Okay, and that's the weighted KLR algebra associated to the quiver. The only thing I haven't told you is how the planar geometry comes into the game, and I will do this momentarily. Let me just repeat what we are seeing, because it's quite a lot of combinatorics to take in. Okay, so we have symmetric group diagrams, certain types of strings, and the strings encode in a very nice way, or in a certain way, the quiver, because the vertices, the labels of the strings are the vertices of the quiver, and the relation depend on the edges of the quiver. So for example, I should have said that anyway, if you are not connected, like -2 and 1, then this relation would just be a plain Reidemeister 2. So you could just pull strings apart. So it really is, so something like this. It really is a matter of the quiver. So you encode the quiver in the relations by deforming the Reidemeister relations. Okay, you can. So the point is, at this point, you should actually complain. What I have said doesn't involve any planar geometry. It's just a more fancy version of the symmetric group up to this point. And I kind of, my bait was, or my idea here that I would like to sell to you, is that there should be some planar geometry involved. It's just, right now, it's just a fancy version of the symmetric group. So why do I bother you with this idea? So here comes how the geometry of the plane enters. It's a little bit subtle, so let me try to, but crucial. So this really is a crucial point. The rest is just kind of playing with diagrams a little bit. Relations doesn't matter so much, but this is a crucial point. So the point is, I will make it such that actually the specific points where the strings are anchored in my diagram, so it's somewhere in R2, or in a little box if you want. So there's somewhere a little box that sits in R2, and I will make it actually the endpoints of the strings matter. And you get different algebras, so non-isomorphic, non-Morita equivalent algebras for different choices of endpoints. So here, I hope I did my homework correctly. My choice of endpoints usually are X, and here I have certain endpoints. So let's say the red string is somewhere here at 0. And I have 0.5, that's a little bit to the right of the red string. I have somewhere pi, oh gosh, pi, somewhere here maybe. Then I have 5, which is somewhere here. I hope you get the point. You have somewhere minus square root of 2, which hopefully is roughly here, and whatever. You have minus whatever. It's roughly here. Okay, so where the endpoints are matters, and you get this huge family of algebras associated to different choices of endpoints. And for certain choices of endpoints, I will make that more precise in a second, for certain choices of endpoints, you get whatever type of algebra. For other choices, you get a different algebra. So the big algebra interpolates in exactly the same way as this interpolating algebra, this toy example, which I'm going to see again in a second, by using the distances of the strings, which is a really, really cool idea. And I've really never seen that anywhere before, except in this setup. And it turns out to be extremely powerful. So here's how it really works, and that's why it's called weighted. Okay, so in order to make this work, so this is the idea, in order to make this work, you kind of need to avoid that strings go freely everywhere, because then you could just rescale your diagram anyway. And the way to do this is to use a weighting of the quiver. That's why it's called a weighted KLRW algebra. It's nothing else than you associate a real number to every edge. So some real number, pi, for example, or -1, or 1, or 0.1. And depending on this value on the quiver, so on the weighting of the graph, you will get different diagrams. And it works as follows. So ignore the red strings, as I said. The main players are the blue ones and the dashed ones, the solid strings and the ghost strings. So whenever you have a value 1 and you have an edge from I to j, what you should do is you have an I string and you put a ghost with distance 1. So this value here goes to here in the distance, which completely mimics the move of the previous string. So we'll see in a second why that matters. So here distance is really low, so you put it, well, this is supposed to be a 0.1 distance here. You put it 0.1. The I string, there's a copy of it, a dashed copy, which is 0.1 units away. Slight catch, which I'm going to ignore for the rest of the talk. There is some convention involved. If you put a negative number, you still shift to the right, which is a little bit counterintuitive, but it makes the algebras a little bit more symmetric. But you shift, in this case, the target of the edge to the right. Okay? So negative number, shift the target to the right. Positive number, shift the source to the right. And you always have the string just mimicking what's going on, the other string. I should have done this one. I should have done this move. Okay, so the weighted KLRW algebra now comes with all those ingredients, this huge input of data, set of endpoints, and a set of weightings, and everything will depend on those choices. Okay, so and the point is
one quick question.
Absolutely.
So in this case, you only put in one ghost string for the pair of vertices, not two. So depending on the number, you put either I or j, not both of them.
That's right. That's right. I have an example on the next slide, which might clear the confusion. So depending on the quiver, so here's an example. For each edge, you put a ghost. So if you have 3 outgoing edges, you would put 3 ghost strings. And depending on the number, you put them either to the source or to the target. So here, I and k, and you have a negative number, so you get a ghost string for k. Here, I and j, and you have a positive number twice, I and l, so you should get 2 ghost strings for I, one of them very close because epsilon is supposed to be a very small number here, and one of them with distance 1. Does it make some sense? Okay, so depending on the quiver, the diagrams will be hugely different. Depending on the choice of weighting, the diagrams will be hugely different. You can have zillions of ghosts. If you have 12 million outgoing edges, you have 12 million ghosts that you would put. And each one of them mimics the behavior of the previous, of the parent string. And the parent string will be either the source or the target. That's a stupid convention, depending on the sign, which it's just what it is. I don't know. But I will use positive numbers in the rest of the talk anyway. So always the source gets shifted for corresponding positive number. 1, pi, 0.1, whatever I write on the edge. And why do I do this? So here's another example before I continue. So here the 1 string, 2 positive numbers, you get 2 ghosts. This is supposed to be 0.7, This is supposed to be 1.5, 1.25, and the other one is 0.75. And all of them mimic the parent string. So why do we do this? Well, that's not some funny behavior, and you can't rescale diagrams anymore, because the following will happen. So if you look at this part of the diagram, you have an I and a j string, then they actually look very close. Well, they look like they're very close. You could pull them arbitrarily close to one another, but actually you can't, because the ghost string will mimic the behavior of the parent string, and you can't pull the ghost strings arbitrarily far together, because the k in the middle just avoids you doing that. And this prevents the whole diagram calculus from being scalable, arbitrarily scalable. It's kind of a fun way of doing it. So locally it looks like everything is close, but actually the ghosts will prevent, because they mimic the behavior, you just can't pull strings arbitrarily around, they mimic the behavior, and they might prevent strings to be very close. So this kind of brings in the whole geometry of R2, and the diagrams are not local anymore, they're really global now, and it completely depends where your strings sit in R2. So all the relations, you might look locally at those pictures and think, oh, I can apply a relation, but actually the ghost strings 200 meters away prevent that from happening. So it's a global information, which is kind of really crucial. So now you have built in the distance in those pictures. And what I mean by scaling is not the overall scale. You can still overall scale everything, but you can't do local moves. You can't do kind of local rescalings. Okay, so really those diagrams are stuck. There's some global information in those diagrams which you kind of build in using this funny geometry of the strings. Okay, I say it again because it's a bit tricky, so maybe this is my favorite as an example for now. You have a quiver, you have orientations on the quiver, you have numbers associated to each edge, and the number tell you where the ghost string go, and the ghost strings will mimic whatever kind of movement you do. So if I have a parent strand that looks like this, then its ghost, which I'm not going to do dashed because I'm too bad, but I just doing it black, will do exactly the same. And there will be some distance between them. It might be very close, it might be very far away, there might be 500 of them, different ghosts, they will get stuck everywhere, and it's really kind of this global behavior that happens here for those algebras. Okay. And the point here is, in my baby example, kind of the position and the ghost shifts correspond to those, so the overall positioning correspond to those roots here that you can specialize to different algebras. So now I can specialize my positions and I will get different algebras. It's kind of the idea. I don't want to be super precise here, but what you could do is, for example, if the ghosts are very, very far away, so you put 1 million on your edge, so all edges have huge labels, then you actually get a semi-simple algebra. If you make your ghosts very tiny, like epsilon, then you get the KLR algebra, and so on. So you can do a lot of algebras at the same time, just by varying somehow all the ghost shifts, all the positions in this picture, which is pretty cool. So you really have this big interpolating algebra, and you can interpolate interesting algebras in representation theory by pushing strings, putting strings at certain positions. It's pretty good, right? And KLR like is very, very close, and semi-simple is kind of the opposite, is very, very huge distance. And you still have one algebra that interpolates between both of them. And whatever you say about this one algebra, you can just push it down to your favorite algebra and get results about your favorite algebras. It's kind of a really nice trick of doing it. Okay. Let me kind of explain, let me push this picture a little bit further, and then I'm going to explain the main result. So kind of cellularity again. So the point is, you can use this to pretty easily write down cellular basis for those algebras, which then kind of work for every choice of involved positions, and you just push them to your favorite type of specialization of the big algebra. Before doing that, let me explain actually how really the geometry of R2 enters this picture, and kind of my picture I want to have in mind, we'll see another example in a second, was also the one I had on my first slide. It's this hyperplane picture. So if I think of this algebra, my interpolating algebra, then basically what happens is you can, of course I should use complex numbers here, but I can't really draw complex pictures, at least not two-dimensional complex pictures, so I stay with the real picture. But basically what happens is you have a hyperplane at A equals B, and everywhere else the algebra will form an isomorphism class or the Morita equivalence class. On those faces you have two different roots, right? A and B are my roots, and also on those faces you have two different roots, and you get all the semi-simple algebras. They are all equivalent. And along with this line here, along this hyperplane, there's this one special case where you get the non-semi-simple algebra, which is this one here. So this one is non-semi-simple, and all of these, doesn't really matter what kind of roots you take, all of them are isomorphic in the end. So if you have two different roots, you get isomorphism classes. If the two roots collide, you get the isomorphism classes for those ones here. Here my roots are 0 and 0, but if my roots would be pi and pi, I would get an isomorphic algebra just by kind of rescaling the algebra. And this is kind of the picture here for this baby case. So actually this hyperplane picture determines isomorphism classes of Morita equivalence classes in general of those algebras. And the same happens for KLR. Just you have, well, for those weighted KLR, just you have a bigger amount of input because it's a bigger algebra. So roughly the picture is the following. So you have hyperplanes according to when strings collide. So let me do the following picture. Here I have the coordinate of the blue string, so this is the blue string coordinate. Here I have the coordinate of the red string, and roughly in this area here I have a diagram like A, where the red string is to the left, the blue string is to the right, and there's some ghost somewhere which I'm not going to specify in this picture. So in B, right, so you just have to swap places. So this one is here, this one is on the right, and in C, so C is so here the ghost and the red string swap places, and this is exactly what happens here. So you have those three regions in this plane given by the cutout equations whenever strings collide, right? So strings might collide, they might have overlapping coordinates, and the type of algebra changes as you move along those coordinates. So you have this hyperplane arrangement given by with hyperplanes given by equations whenever strings collide. So the first equation here is solid in red, that's why I denoted by SR. This would be exactly the case. So on this hyperplane there would be the diagram where the red string and the solid string are exactly at the same space. So the step from going from here to here is exactly kind of this swapping picture. Okay. And then the statement is that you get actually those algebras who cut out all of these equations. There's a high-dimensional space, and they give you a lot of hyperplanes, and in each connected component of this space you have a Morita equivalence class of those algebras. So roughly the picture you should have in mind, this is a non-example, so the equations are too high-dimensional to really, for me to really illustrate a two-dimensional example, but basically it should work as follows. So we have some hyperplane picture with some equations cut out by the strings, and somewhere is a KLR algebra, somewhere is a semi-simple case, and the other algebras are somewhere else. And you can connect those algebras by certain types of translation type functors which jump over those hyperplanes. Okay, but the point here is that the distance is really encoded in this picture, and it really matters when you kind of swap the order of strings, and you get different Morita equivalence classes of those algebras with certain choices corresponding to KLR algebras, certain choices corresponding to semi-simple algebras, certain choices corresponding to a different family of nice algebras, and so on. And the big algebra kind of interpolates between all of them, because the big algebra is just a huge beast, and for your choices, in a very controlled way, in this hyperplane controlled way, for different choices, you get different algebras. It's kind of a really nice picture. It really is a generalization of this picture if you want. So the hyperplanes cut out Morita equivalence classes of those algebras. And the hyperplanes are just given by whenever strings collide. And this is how you now interpolate. So this is kind of this distance idea, how you can interpolate between those various algebras. And each one of them, as I said, corresponds to a connected component of this hyperplane picture. Again, a matter of warning, usually those pictures are hugely high dimensional and I just can't illustrate them. So this here is it's a non-example. I didn't took any real data here. It's just the numeric to keep in mind. Okay, great. So this is kind of the main setup. So we have this algebras where distance matters in a certain type, and Morita equivalence classes of those algebras are determined by some nice hyperplane geometric picture. And those algebras that turn up in categorical representation theory are all special cases corresponding to connected components of this picture. That's actually already pretty nice. I think that's a pretty nice setup. And the point now is, of course, that you hope, and that's actually true, that the big algebra is somehow easier controllable than the small algebras. And you have a statement, you prove it about the big algebra, you push it down to your favorite specialization, and there you go. You have a new theorem about whatever, KLR algebras. Okay, let me just make this a little bit clearer now. Certainly for some of the experts here in the audience, that I'm slightly, let's say, I could be more precise in my language. So KLR algebras come in two different types. There's an infinite dimensional version and there's a finite dimensional version. The finite dimensional ones are called cycloatomic quotients. And again, you can use the distance of those diagrams to define cycloatomic quotients, and it works as follows. So if you never heard about cycloatomic quotients before, here's a diagrammatic definition. So you take your diagram, and this is where the red strings now come into the game. Before, the red strings weren't just around, they were not so interesting. But now you have some red strings somewhere, whatever, and you have some blue strings and you have some ghost strings. God knows how it looks like, something like that. A huge mess. Whatever, something like this, a huge mess. And you call a diagram unsteady, and these are the ones you would like to kill because they are unsteady if there is some string you can pull arbitrarily far to the right. Okay? So in this case here, I could pull my blue string arbitrarily far to the right. Why can I do that? Because my ghost here would just mimic my blue string, and the red just stays where it is. So I could just pull it arbitrarily far to the right. And here I can't do that because I at one point get stuck at my red string. And this defines an ideal in this algebra by the unsteady diagrams, and if you kill those, you get the cycloatomic quotients of the KLR algebras. And you now have a beautiful and very geometric interpretation of the cycloatomic relation. It's just the diagrams that are very, very far to the right. And of course, to the right is a choice here, because my whole setup is somehow biased to the right. You could do a left version as well. But the point is, as soon as strings pull freely, it becomes unsteady, and you kill those, and you end up with the so-called cycloatomic quotients, which you can then fairly easily show that they're always finite dimensional. And many more properties depend on those distances, and you can just use the distance to play around with a lot of properties of those algebras. You can write down bases and so on. For example, you can write down cellular bases given by a certain type of minimality relation, which I'm going to explain a little bit in the remaining 10 minutes. Right? So the point is, let me repeat that. I just listed two examples here, and I'm going to explain the cellular part a little bit more in details. So cellular is exactly what you know from last time, so somehow nice bases associated to those algebras, and all of them you can define them and prove everything, all properties about them, just using this idea of distance, and many more, which is kind of naturally built into those algebras. Remember that the Morita equivalence classes of those algebras are determined by how far strings are apart and where they really sit in the diagram. So it really comes really naturally in this picture. And you get beautiful diagrammatic interpretations of really non-trivial facts about those algebras. Okay, let me now come to the... I need to be a little bit sloppy here now because I only have 10 minutes or so left. But basically the point is the following. For the weighted KLRW algebras, it's extremely easy to write down cellular bases. It's extremely easy to write down standard bases. Basically what you do is you put some idempotent at the bottom. Maybe I shouldn't use red strings. You put some idempotent on the bottom, so these are just random strings here, and you put some permutation on the top and do that in a controlled way, and you get actually a basis for the algebra. And in a very similar way, you can define a cellular basis. So you put some idempotent in the middle, and an idempotent is just a bunch of, what is it, vertical strengths, I guess. You put some permutation nonsense on the top, and some permutation nonsense on the bottom in a controlled way, and that's a cellular basis. And how do you ensure that this is a cellular basis? If you remember, cellular basis basically is the following idea, that you have a matrix in the basis elements, such that multiplication, those blocks are the various cells in the setup, and multiplication should get you always somehow up, such that you have unitriangularity built in. So there's some order in the cellular relations, and this is like this picture of having block diagonals, and multiplication gets you to the top, and you have just zeros down here. And the order, what could the order be in this case? I mean, distance. The order is how far strings are to the right, and the cells in this case is kind of determined by how far strings are to the right. So depending on a certain type of numerical invariant. So strings are this far to the right, you are in this cell. Strings are this far to the right, you are in this cell. And multiplication increases strings because you can always somehow pull strings further to the right. So here's an example of this, how this is supposed to look like. So here's a permutation diagram which I call T. So it's just this part. Here's a permutation diagram that I call S, just a permutation. And in the middle you have an idempotent diagram, which the whole point is you kind of push it as far to the right as possible. And depending on how far it goes, it gets stuck somewhere, and that's the cell where it lives in. So you can produce those idempotent diagrams by using the distance, by pushing everything to the right as far as you want to. So this is kind of the general setup, and the point is, I don't expect you to understand all the combinatorics now. The point is, it's again distance, and you can make everything work in terms of distance, and all the notions from the general theory of cellular algebras have a nice interpretation in terms of distance for those algebras, depending on where your strings sit, whether they're very far to the right or kind of some mixture of everything. Okay, so really distance is it. That's the whole setup with the KLRW algebra. Everything you want has a nice distance diagrammatic, distance geometrical interpretation. Everything. Okay, and the point is, so I think this should work in pretty much generality to write down cellular basis for those. We haven't done that, so we only have done it for certain types. Okay, fine, but I'm pretty sure that it works in quite some generality. And the kind of idea here, again, for the experts is, because you have all these nice interpretations of everything in terms of distance, you just write it down for the infinite dimensional algebra, and the cycloatomic one comes for free, because you just kill diagrams that are too far to the right. That's just how it works. Okay, let me just say there's some work in this direction by Chris Bowman and Ariki Park and Speyer, which kind of constructed just the Specht modules in the setup, so the cell modules if you want, and this kind of then proves cellularity, which is one of those results which you easily push down from the big one to any of the others. Actually, it's kind of general way of proving cellularity for all of them. As I said, it should work for all types. Right now we only know it for those types actually. So when our approach works, but both in the infinite dimensional and in the finite dimensional, in the cycloatomic case. I'm pretty convinced that finite types will work, but I need to write that down. I'm pretty convinced that all affine types will work up to a certain degree, but again, everything combinatorics get a little bit tricky because those algebras are already a little bit tricky. But the overall setup is pretty clear and I think quite nice. So you kind of you kind of have a notion of distance and reflects the different cells in the cellular algebra. And the order in the cellular algebra is just how far strings are to the right. That's just what it is. Alright, let me just explain the construction in one type. Don't worry about too much. I just want to do this type, and I just need to say here that everything is actually super explicit. So we have SageMath code, so you can just run SageMath and it will spit out the diagrams, it will spit out the basis. So it's super explicit actually. And it works roughly as follows. So I'm only staying in this type because somehow the code is best for that type. Don't ask me why. I should have cleaned up the code for all other types as well, but I don't know. Anyway, I would stay in this type, and if you don't remember what this is, it's just a double edge, then a lot of single edges, and then a double edge at the end. So it's called affine type C. Okay, fine. Again, don't worry about affine type C. The point is, in this case, my code works best. That's just what it is. But the idea is always the same. So we know cellularity in those types. As I said, I'm pretty sure about other types as well. So here, this one is the one I'm looking at right now. Again, it works as soon as you have the infinite dimensional case. The finite dimensional one is just a corollary. Pretty simple. Okay, so I'm focusing on this quiver in my last 4 minutes. The point is, in this whole construction, it's kind of always the same idea. So you can write down the permutations in a very controlled way. They're pretty harmless. There are some tableau combinatorics associated to it. It's pretty straightforward, pretty explicit, not going into details. The point is the construction of the middle. As soon as you have constructed the middle will index the cell. Right? The middle is the kind of, in my matrix picture, the middle is whatever you see on the blocks. It's really the important part of the game. The rest is just decoration to make everything work. And I would like to focus on the middle. Mostly because I only have 3 minutes left. So, okay. So middle is the main part. As soon as you can construct the middle, the rest is kind of easy. Again, maybe I should have said that. In general, it might not be super easy, but at least in our setup, it's really, really easy. As soon as you've constructed the middle, all proofs just write themselves. Okay? There's almost nothing you need to do. I'm not going into too many details. Obviously, I don't have any time, but I will explain in a second where the middle is supposed to come from. Basically, you place strings inductively as far to the right as possible. So you have some associated combinatorics. You read along your combinatorics. So you would like to place a 0 string, you would like to place a 1 string, you would like to place a 2 string, and so on, and you read along those combinatorics, and you just place them in order as far to the right as possible. Give you an example in a second. And by construction, this diagram is minimal in the order, because the order is just how fast strings are to the right, and that's what you need to prove cellularity, and you don't really need anything more. Which is kind of a very surprising way of doing it. Let me just show you an example. Maybe that's clearer. So let me skip this one. So here, for example, this diagram works as follows. So I put a 0 string, then I put a 1 string, then I put a 2 string, then I put a 3 string, and how many strings do I have here actually? 1, 2, 3, 4, 5, and then I put a 2 string again. And this works as follows. So I have somewhere my anchor, okay, it's just somewhere, who cares? And you put the first string a little bit to the left of that anchor. Okay? The first string you put has some ghost somewhere. Okay, this was this string, done. Next string, you put it a little bit to the left of the previous string. So it gets stuck after that string. It has some ghost somewhere. Okay, this one is done. Next one, maybe I shouldn't use blue. 2, the 2 comes a little bit to the left of the previous string. And you keep on going. You have some bouncing back here because the 2 won't have a ghost, but don't worry about it too much. So you just keep on going, just place a string at the rightmost possible free slot, keeping some small distance from the previous strings. You can do that for all those things, and you get diagrams that look like this. And all of them were created using code. So it's actually pretty simple. I mean, you can tell a computer how to do that, right? Place a string as far to the right as possible. And that's the middle of your diagram. And you can do that in any type you actually want. And the only point you need to be careful is to just prove that everything works, and we can only do that in the types mentioned before. But the idea is the same everywhere. You just place strings to the right as far as possible. Yeah. And so let me just wrap up. So this weighted KLRW algebras, they generalize KLR algebras and many more algebras using this idea of distance, and all properties basically can be read off from this distance, and most of them are actually type independent, and you can prove all the properties with just using some, I can pull strings to the right argument type of argument, which is pretty simple. A final thing I've probably stressed that already, but let me stress it again. Our approach is very applicable to computations, and in all finite types. For example, we haven't worked out all the details yet, but it will work in finite types as well. And computations we can already do with a machine matches the formulas you get for the. If you specialize to this KLR case, actually it matches the nice formulas by Hugh and G, which they worked out about a year ago or so, maybe not quite. As really beautiful formulas, they get them from completely different points of views, and using our combinatorics, we get exactly the same formulas basically. And that's what I wanted to say today. So thank you very much.